Today we're going to work out an example of a double integral that would require, or I shouldn't say require, but be much nicer to do if you change the variables appropriately. Here's our integral, dA, and where R is the trapezoid, whose vertices, we'll say it this way, whose vertices are 0, 0, 5, 0, 5 halves, 5 halves, and 5 halves, negative 5 halves. Okay, so if you take a minute to draw this, you'll get a sense of why you might like to have a change of variables. So let's consider. So first off, here's 0, 0, here's 5 halves up here. So you can tell right away that's the equation y equals x. That's the equation of that line. And then 5, 0 is out here. There you go. There's that line. That line also has a slope. That line has a slope of -1, but a little bit of work, you'll see that equation has a y-intercept of 5. And here's the other part. This is 5 halves negative 5 halves. Y equals negative x. And then over here, you end up with y equals x minus 5. All right, so this region, this trapezoidal region, is the thing that we're finding this double integral. All right, so you can tell, even if we decided to do this as a type 1 integral, an integral where we do dy dx first, maybe, if we do that, then you can tell there's a line down the middle, and on the left side of that line, this is the upper curve. Well, this is the upper curve. And then when you go over to the right side of the line, there's a different upper curve. Notice this equation here dramatically. So if you're going to do the integral this way, you're going to have two integrals. And then they'll need to be added together. Get it? And the problem doesn't change if you try and do the integral dx first, you'd have a line like this, horizontally. And then when you do right minus left, here's the right, here's the left. But for below the x-axis, here's the right here. So a change of variables might be nice. All right, so I'm going to present you with maybe you could think about where it came from and why it works. But here we go. So x equals 2u plus 3v. And y equals 2u minus 3v. We're going to use those transformations. So what you can do is basically take each side of this region and transform one at a time. So we're going to start with y equals x, and go to y equals negative x, and we'll go up here, and then transform to the side to see what that is. So using y equals x, and these transformations, you end up with 2u minus 3v equals 2u plus 3v, where 6v is 0, v is 0. So that's a much nicer bound. All right, let's consider y equals negative x for a moment. So you have 2u minus negative plus 3v. And to do that, we end up with 4u equals 4u. That's nice. Let's keep going along here. If you do y equals negative x plus 5, we end up with 2u minus 3v equals the negative of 2u plus 3v plus 5. All right, so that looks a lot like the equation above it, except this is plus 5 on the end. So you end up with 4u on the left, but 5 on the right instead of 2. So u is 5 fourths. What you notice now is my bounds for u and v are shaping up to just be constants rather than variable expressions. And then lastly, I have y equals x minus 5. You have 2u minus 3v equals 2u plus 3v minus 5. End up with negative 6v equals negative 5, or v equals 5/6. So pretty nice limits of integration here. Okay, so what can we say in summary? What we just found out is that u is always between 5 fourths and 0, and that v is always between 5/6. and 0. Right, so we're ready to rewrite our integral. So our integral is going to look like this. 0 to 5/4, 0 to 5/6. That's going to be the u dv with one small issue. That is, we need a correction factor. Well, actually, we need two things. First off, we need to rewrite the thing we were integrating. It was x plus y. You take a minute and plug in your transformation of variables. This is what you get. Well, we add them together. That's just 4u. And then additionally, we need the Jacobian, we need the correction. Jacobian is going to look like this. Partial x, partial u, partial x, partial v. And then here, this is going to be partial y, partial u, partial y, partial v. So if we just go through and do that, if we look at the transformation next to it, it'll remind you what it was. Transformation, well, this piece right here is equal to x, and that piece is equal to y. So here we go. We'll apply those together and get our Jacobian. So partial x, partial u is 2, and then partial x, partial v is 3. Partial y, partial u is 2 again, and then partial y, partial v is negative 3. All right? So we do our determinant here. We get negative 6 minus 6, or negative 12. Take the absolute value, that becomes 12. That's the value of our Jacobian, and that is our correction factor. We'll put that in here. And now we're all set to go. And if you look at this integral, first of all, there's only one integral. And the limits of integration, you'll notice, are constants. So this is really not complicated compared to the way we would have had to do it otherwise. Let's do this. This is going to become 48u du dv, which goes from 0 to 5/4, 0 to 5/6. All right, so we'll finish this up in a couple of minutes. The first antiderivative is going to be 24u squared, evaluated from 0 to 5/4. You do the math there correctly. You'll get 72/5. And now we'll do the integral from 0 to 5/6 of 75 seconds. That's my bad. 72/5. 75 over 2. 75 over 2 dv. And even these antiderivatives are fast. That's just 75 over 2 b. 5/6. We plug in 5/6. We end up getting 125/4. There you go. That's how you can use a change of variables and Jacobian to find the value of a double integral. There's many examples. If you send me one, I would do it. I'll put the video online. Thanks for watching.